The world hates change, yet it is the only thing that has brought change. This is how change powers change, in the words of Charles Franklin Kettering, a leading innovator at Ford Motor Company in early 20th century. Indeed, the reality is, nature is in a web of relationships that involves the rate of change of things or situations influence change in something else. Mathematically, it demands that we must be able to write functions that have dynamic or changing variables in it. That is to say, functions may contain the derivatives of variables, not just the variables. Recall, functions mathematize the real-world relationships, and they are mostly in the form of equations. Concisely, equations that have terms that are the derivatives of variables are called differential equations. In the two preceding lessons, we explored differentiation and integration. Together, they quantify continuous change by capturing just the two things we need to know about such changes: the state of change at any instant and the cumulative effect of change over an interval or the entire span. The two are closely related. In fact, differential equations bring together differentiation and integration to quantify the varied and changing real-world situations. Differential equations denominate scientific research and laws as much as the man-made world of technology, engineering, and all kinds of research. The world of differential equations is all of the real and man-made world. Next, we will explore a few situations which deploy differential equations. The first example of differential equations is a conceptual one, but something that does bring out the essence of changing quantities and conditions that continuously affect something else. It is the universal personal experience of change in our body temperature in response to changing conditions outside and within the body, such as the ambient temperature, metabolism, hydration level, the type of activity performed during a particular time, and more. It is not a mathematizable relationship yet, but it is most easily associable, appreciable. The second example of the application of differential equations is the equation that can help us calculate the time required to drain a tank full of a fluid. In equation terms, factors like the size of the hole for draining and gravity are constant terms for a specific tank. Density and viscosity of the fluid are variable characteristics, but the volume of the fluid, the head pressure, and flow dynamics sure are key characteristics that continuously change with time as the fluid flows. Recall, any equation, including differential equations, have constant terms, variable terms, and ever-changing derivative quantities. The equation is an example of a differential equation for such a situation of flow. This situation is best captured by differential equations, and such equations have constant terms, variable terms, and ever-changing derivative quantities. In this example, the head pressure, or the pressure of the fluid quantity left at any instant over the drain hole, is one example of a derivative quantity. The third example is that of the use of a set of differential equations in the architectural and civil engineering design of earthquake-resistant buildings. There are physical principles and considerations called structural dimensions of buildings. Scale and shape are broad examples of such contexts. Then there are special stabilizing factors in building design and construction called the damping mechanisms, including material damping. Of course, the ground motion acceleration function of earthquake at different scales is also a part of the whole design. A generic differential equation is presented here, the form and details of which are irrelevant. This example is to show how differential equations are framed or expressed. We can see that it has double derivative, single derivative, has variables and constants. It is a sum of multiple variations, duly weighted for the net impact. In this equation, for instance, M is the mass of the building as a matrix or multipoint, C is the damping matrix, K is the stiffness matrix of the building. The variable X is the displacement vector, or simply speaking, force. Interestingly, this equation is like the generic mass spring damper system equation. This is a humbling feature of nature and mathematics. We can identify a set of kind of parent equations which forms the basis of the widest set of differential equations in application. I also take this example as an opportunity to briefly mention how differential equations are otherwise routine mathematics. For instance, the double derivative in the equation is to be expected in the play of force and a mass. The use of double derivative in the equation is how we express the impact on mass over time. It derives from the Newton's second law, wherein the net force acting on a mass causes it to accelerate, a double derivative of displacement. On the other hand, the damping force is energy management effect, and thus proportional to velocity, the single derivative of displacement. The fourth example of differential equations is how we compute the value of the national income of a country. The latter is dependent on various factors that are fundamental or constant in shorter term, as also those that are variable in terms of absolute levels, and some others that continuously change even in the short term and continuously affect other quantities. In equation terms, national income is determined by consumption, investment, labor participation, sophistication of technology and engineering, inflation, external trade, etc. The differential equation of national income is expectedly complex, but it is often simplified for specific measure of national income levels and changes in it. The details of the symbols are just out of the scope of this discussion. An important purpose of presenting the four examples was to distill the common, characteristic features of differential equations from the illustrated instances. The following three key takeaways are apparent. First, differential equations are like arithmetic and trigonometric equations with one difference. There are terms that are derivatives. We have witnessed the same in the examples. Second, a small set of equations are used as the skeletal equations for developing meaningful differential equations. We talked about how the differential equations of earthquakes' impact on buildings are akin to the general mass spring damper system equation. Even the national income differential equations are derived out of the Cobb-Douglas production function. The Cobb function is extensively used in most economic input-output relationships, such as in a manufacturing setup. Third, the solution of differential equations is an equation that has no derivatives. It is the kind we are familiar with, the arithmetic or trigonometric function. Why? Because that is how we can generate outputs for different inputs from the real world or the man-made world, such as technology or social sciences. We shall now focus on concisely exemplifying how a small set of equations generate a wide range of differential equations, and how we use differential equations to get the familiar equations to use them as normal functions by integrating them to solve them. Two other observations may also be made. They may not be directly inferable from the examples, but the two are relatable with some reflection. Unlike algebraic equations, the solution of differential equations is not a quantity but another function. Differential equations give us a modeled behavior of things, not a particular instance of behavior. Differential equations are truly functions in the sense that they represent a range of input-output processing. Before we get on to explore the basic set of differential equations that prop up the extremely diverse world of differential equations, a quick recall of equations as relationship expressors might be helpful. Consider an example of a mother who is 6 times the age of her son as of date. But in the next 5 years, she will be 25 years older to her son. What are the current age of the son and the mother? So we need the equation equivalent of this age relationship of a mother and her son. As shown, 2 equations are needed to express the 2 conditions. The first, 6x is equal to y. The second, x plus 5 plus 25 is equal to y plus 5. We then solve the 2 equations, which are simultaneous or concurrent, so to say, to get the value of x. The current age of the son and the value of y, the current age of the mother. Let us exemplify how only a small set of differential equations, or equations with derivatives, lays the foundation of the application of differential equations across domains of our world. We will present examples of both ends of this feature. First, we will showcase a simple differential equation that closely represents many disparate real applications. Next, we will list some of those more common differential equations. The differential equation dy by dx plus x is equal to 2 is a simple linear differential equation. Infinite variations of this form of differential equation, called the first-order linear differential equations, are possible. Such equations are just the ones to study and mathematize certain behavior of many real situations. For example, this linear differential equation is the one used for representing steady-state fluid flow, control systems of aircrafts, models of economic growth measure, voltage across inductors or capacitors in electric circuits, effectiveness of drugs in terms of presence in bloodstream, and the pricing of certain investment instruments. The list is obviously endless, and this is such a commentary on the nature of nature, the extensive simplicity and specificness of logic and actions in nature, and the connectedness of it all, changes driving changes. Now let us get a list of commonly used differential equations. Two aspects must be clarified before we list. First, each of these equations is a source of infinite applicability in best-fitting mathematics to the infinite realities. We will explore this next. Second, the differential equations, broadly speaking, are also often used as source for numerical methods, rather than being applied as a formula. We will also touch upon this to complete the appreciation of differential equations. Here are a few of the common equations. Heat equation, second law of motion, simple harmonic equation for motion of springs and pendulums, wave equation, exponential growth or decay equation, linear differential equation by itself, Lotka-Volterra equations that model ecological play in terms of predator and prey interactions, or Bernoulli equations. There is little point in listing the equations. Let us now seek how one of the equations, the Newton's second law of motion, is variedly used. Clearly, the equation is the way we determine the velocity and position of an object in free fall motion. It also describes simple harmonic motion. A slight variation in the equation helps us model the motion of a rocket as it accelerates and loses mass due to continuous consumption of fuel, for instance. Another variation in the equation helps us model the trajectory of objects under gravity and air resistance, routinely used in some sports, for instance. A micro-detailed form of the equation helps us analyze the effects of various forces acting on a body in motion, such as friction, fluid drag, etc. A modified version of the forces form of the equation is also used for studying the motion of the limbs in specific conditions, such as that of athletes in action. Duly adapted form of the equation is extensively used to model electric current and voltage in circuits. Another adapted version of the equation helps build simulation for the nature of vibrations of a building under seismic activity. The list is far too long if we also consider the possible variations in each of these applications. Interestingly and importantly, the power of differential equations in mathematizing reality extends beyond its solutions, that is, beyond the equations, or formulae we get from solving them. When we work with equations, we say that we are operating analytically. Not all differential equations can be solved for analytical use, that is, assuredly be derivable to workable or simple equations. For example, many variables, highly nonlinear reality, or imprecise initial or boundary conditions may render equations difficult for Roper solution. However, in such situations, we directly use the equations as a means for step-by-step, simple numerical computations towards approximate, not exact, solutions, and in many cases the approximate is useful enough. Here is an example of how this numerical computing works. The first equation is the equation to analyze population growth. The second equation is the exact or analytic solution of the first equation. By direct substitution of the initial population and the growth rate, we can find the population size at any time. The third equation is the more realistic growth equation. For example, it factors in the carrying capacity, reflecting the limitations imposed by the environment on population growth. The fourth equation is the numerical computation of the increased population day by day. It shows the increased population at the end of the first day. The fifth equation is the numerical computation of the increased population at the end of the second day. We now need to know how we use differential equations. We solve the function that differential equations are to get a derivative less function, a function that does not have derivative terms. We cannot directly apply differential equations unless and until we convert the derivative terms into derived functions and simplify the full differential equation to one integrated standard form of equation. Recall, the derivative of a function is also a function. Once a differential equation is solved into a standard form, it can provide predictions about future behavior. This is highly desirable or even essential for all situations. Knowing how situations or things is likely to behave under different conditions is valuable for all the reasons. Three different kinds of differential equations and their general solutions, all derivative-free, are shown. The solutions are arrived at by integrating the equations to rid them of derivatives. In a later lesson, we will learn how multi-term differential equations are much like multi-term arithmetic equations when we solve them, and that will complete the understanding of solving differential equations. It might now be somewhat obvious that the applications of differential equations extend far and wide, and they are the best for capturing, modeling, and analyzing continuous change. Yet briefly, differential equations are not the only way to model real-world phenomena or situations. Simple algebraic equations, statistical methods such as measures of centrality, deviation, probability theory, graph theory, game theory, Fourier analysis, etc., are as real as it gets. They are based on real data. However, these are better for discrete events and situations, and they are useful to a world of reality by themselves. There is just another significant phase of differential equations. The distinctions that emerge between differential equations primarily due to the number of variables involved and the number of variables that fully explain a situation or a thing. An ODE, or an ordinary differential equation, is a differential equation that contains one or more derivatives of a single independent variable. Examples are showcased. A PDE, or a partial differential equation, is a differential equation that contains one or more partial derivatives of multiple independent variables. Examples are showcased. Next, we will exemplify the two with a simple real-world example each, but after we have an example that exemplifies the distinction between the two. Imagine planning a vacation. An ordinary differential equation for this planning may be around the monetary budget, especially if money is the overriding consideration. On the other hand, a partial differential equation would take into account multiple parameters: monetary budget, personal preferences, experiences sought, duration, co-travelers, etc. Now, it is obvious that the second equation will optimize vacation goals with respect to the multi-goals, but it is more complex and needs far more clarity of priorities and knowledge about everything involved. A simple example of ODE is the population growth modeling, to get to know the dynamics of populations. Imagine a population of bacteria in a petri dish. If we assume that the bacteria reproduce continuously and that there are no limits to resources like food and space, we can easily and reliably model the population growth by a differential equation. Of course, in reality, it does get complicated. For instance, such models are truer for microbes. They reproduce faster, and mostly over shorter periods because resource constraints kick in after a while. A simple yet significant example of PDE is the heat equation, which describes how heat diffuses through something over time. It is about modeling how the temperature varies along the length of a straight metal rod over time. This is after one end of the rod is heated at some instant, while the other end is kept at a constant lower temperature to start with. This equation shows continuous change with respect to two variables, time and space, that is, along the length of the rod. The first partial derivative of temperature is with respect to time and shows how temperature changes over time at a fixed position. The second partial derivative of temperature is with respect to the length and shows how temperature changes along the rod at any instant. Thus, PDE helps us get to express the rate of change in very specific ways, in ways that is most real. Differential equation is the quantitative language of continuous change situations. It uses derivatives for its expression and integration for its solution. The solved differential equations are directly usable functions. A set of differential equations is good enough for many needs of analytically expressing reality using differential equations. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.